ready for takeoff.
Hello, RubyConf. My name is Peter. I'm on the Ruby core team, and I'm a senior developer at Shopify based out of Ottawa, Canada. Today, I'll be talking about why 1.5 is the midpoint between 0 and infinity. So what do I mean when I say that 1.5 is the midpoint between 0 and infinity? It all started when a coworker asked this question on Slack. Why is 1.5 the first number Ruby's binary search inspects when searching between 0 and infinity? And attached this code snippet. The question and the code were both a bit odd to me, because how can you search over an infinite range? And how is 1.5 related to this in any way? Well, let's first take a look at this short Ruby code. It's first creating a range between 0 and infinity. It's then calling the range bsearch method over that range. We then output every number that we inspect, and then the block returns a Boolean, whether the floating point number passed in is greater than 42 or not. Essentially, we're looking for the first floating point number that is strictly greater than 42. Now let's run this script and see the output. We see a lot of numbers that it inspects, with the first number being 1.5. Followed by a lot of very large numbers that are seemingly random, and then we see the numbers converging closer and closer to 42. So how does range bsearch figure out what numbers to inspect here? In order to understand this output, we first have to understand how binary search works, and then how floating point numbers work. But before we talk about how binary search works, let's talk about how linear search works. It's really simple. We simply just inspect every element in a list and compare whether or not it's equal to the element we're looking for. Let's look at an example. Let's say we're trying to find the number 15 from this array of integers. With linear search, we simply scan from the start of the array and check if each element is equal to 15, the element we're searching for, until we find the integer 15 in our array. Simple, right? Now let's see how binary search works. However, before we can do that, we need a restriction on the list that we're searching over. It has to be sorted in either ascending or descending order. Let's see an example using the same array of integers, but sorted in ascending order. Again, we'll try to find the integer 15 from this list. To use binary search, we need to have two cursors. A low cursor that points to the first element of the array, and a high cursor that points to the last element of the array. The two cursors define the window which we're searching over. Using these two cursors, we'll calculate a third cursor called the mid cursor that points to the element at the midpoint. We compare the value of the element at the midpoint to 15, the number that we're searching for. Since 48 is greater than 15, we move the high cursor to the mid cursor. In a single comparison, we just halved the number of elements we're searching over, because we know that 15 must be in the window between the low and the high cursors. And we repeat this process again. Using the low and the high cursors, we'll calculate a mid cursor at the index halfway between them, which is at integer 12. We'll compare 12 and 15. Since 12 is less than 15, we'll move the low cursor to the mid cursor. Once again, this comparison halved the number of elements we're searching over. And we repeat this process once again. Using the low and the high cursors, we'll calculate a mid cursor at the integer 15, compare 15 and 15. Since they're equal, we found the elements we're searching for. In the time it took me to explain binary search, I could have probably explained linear search 5 times. It's so complicated, so why do we use it? Because if the list is sorted, then binary search is much faster, especially when we're searching over a large number of elements. Take a look at this graph. The horizontal x-axis shows the number of elements we're searching over, and the vertical y-axis shows the number of comparisons we have to do in the worst case. For the computer scientists here, you might have heard of the big O complexity, and that's what we're graphing here. For linear search, we have to do comparisons equal to the number of elements we're searching over in the worst case. And this is graphed here as the red line. For binary search, since every comparison halves the number of elements we consider, this results in comparisons equal to the logarithm of the base 2 of the number of elements in the worst case. This is graphed here as the blue line. We can see that the blue line is significantly lower than the red line. For example, for an array of 100 elements, linear search would have to do at most 100 comparisons, whereas binary search would only need to do at most 7 comparisons. We just looked at how to perform binary search over a sorted array, which has finite size and definite endpoints. So now you might be asking, how can we perform binary search over floating point numbers? There seems to be an infinite number of floating point numbers. And on top of that, we're binary searching between 0 and infinity. So how is infinity a finite endpoint? In order to understand how we can binary search in a range between 0 and infinity, we first have to understand how floating point numbers are represented internally. In particular, I'll be talking about how IEEE 754 floating point numbers are represented. All modern CPU architectures we use nowadays, such as x86, ARM, and RISC-V, all use IEEE 754 floating point numbers internally. So what I'm about to show you applies to all modern computers. For simplicity, I'll be talking about 32-bit floating point numbers, also known as single precision floating point numbers. However, Ruby uses 64-bit floating point numbers internally, also known as double precision floating point numbers. They both work in the same way. It's just that 64 bits will be able to represent more precision than 32 bits. There are 3 parts to an IEEE 754 floating point number. So one way to explain how these 3 parts work would be to throw a formula like this at you. However, I find this to be unintuitive and difficult to understand. So I'll move this off to the side, and I'll try to explain this using a different approach. So first, we have the sign. This one's pretty self-explanatory. It's a single bit that's 0 when the number is positive and 1 when it's negative. It's then followed by the exponent. The exponent is 8 bits in size, meaning that the value can range between 0 and 255. Intuitively, the exponent tells us the range which this floating point number falls into. Ranges start at the power of 2 and end at the next power of 2. Compared to using something like, say, linear ranges, using powers of 2 will let us represent both very large and very small numbers in magnitude. This table shows some of the exponent values in decimal on the left and the range it corresponds to on the right. The square bracket on the left-hand side of the range means that the starting point is inclusive, and the round bracket on the right-hand side of the range means that the endpoint is exclusive. Ranges start at 2 to the power of the exponent minus 127 and ends at the next power of 2. We subtract 127, so we are able to have ranges to represent numbers with magnitudes between 0 and 1. For example, an exponent with value 125 starts at 2 to the power of negative 2, which is 0.25, and ends at 2 to the power of negative 1, which is 0.5. Now that we know the range that the floating point number is in from the exponent part, the significand tells us where the number is in the range. Using 23 bits, the significand can range between 0 and 2 to the power of 23 minus 1. This divides the range into 2 to the power of 23 parts, which is about 8.4 million parts. The significand tells us how far into the range the floating point number lies, and the significand splits the range into 8.4 million even parts. It's interesting to note that because the significand can only divide the range into a finite number of parts, it means that certain numbers cannot be precisely represented as floating point numbers. You can actually see the consequences of this. Try opening up IRB or a Ruby script and try to add 0.1 and 0.2. You'll get a result that's not quite 0.3. Why this is left as an exercise for you to think about after this talk. Let's see an example of a floating point number. Let's try converting this floating point number, which is in binary, into a decimal number. We see that the sign is 0, meaning that this is a positive number. Now let's convert the exponent into a decimal number. It's the number 130. This corresponds to the range that starts at 2 to the power of 3, which is 8, and ends at 2 to the power of 4, which is 16. The significand corresponds to this decimal number, which is about 2.6 million. To get how far into the range between 8 and 16 this floating point number is in, we divide this number by the 2 to the power of 23 number, which is this 8.38 million number. And we get 0.3125. This means that we are 31.25% of the range between the range 8 and 16. And we can calculate this to be the number 10.5. So these bits represent the number 10.5 in floating point. Now that you've seen how binary search works and how IEEE 754 floating point numbers work, let's see how these two concepts tie together. But before we can tie binary search and floating point numbers together, let's look at how the special floating point numbers 0 and infinity are represented. For 0, it's simply represented by all of the bits being 0. For infinity, it's represented by the exponent being all ones and the significand being all zeros. Note that this is the largest possible floating point number, since IEEE 754 uses an exponent of all ones and a non-zero significand to denote the value not a number. This value is used to signal that this floating point number is invalid. All right, let's go back to these two numbers. And let's try to do something that's perhaps a little strange. What if we read these floating point numbers as if they were 32-bit integers? For the floating point number 0, it'd simply be 0 as an integer. For the floating point number infinity, it will be this number that's about 2.1 billion. Again, it's important to note that what we're doing here is we're directly reading the bits of the floating point number as if it was an integer. And this is different than casting a floating point number to an integer. We cannot cast a floating point number's infinity into an integer, since integers do not have the concept of infinity. In Ruby, if you try to convert infinity into an integer, an error will be raised. In the C language, however, it will result in undefined behavior, and the result will depend on the system. All right, let's make some space. And let's try to calculate the integer that is at the midpoint between 0 and 2.1 billion. It's this number that is 1.06 billion in decimal. We got this number by adding 0 and this 2.1 billion number, and then dividing the sum by 2. This integer looks like this when we convert it into binary. Now let's take a closer look at this binary number. And let's try to convert this integer back into a floating point number. The sign here is 0, meaning that this is a positive number. The exponent is 127 in decimal, which means that the range starts at 2 to the power of 0, which is 1, and ends at 2 to the power of 1, which is 2. And the significand is this 4.19 million number in decimal. We can divide it by 2 to the power of 23, which is this 8.38 million number, and we get 0.5. This means that we are halfway in the range between 1 and 2. And we can calculate this to be the number 1.5. Ladies and gentlemen, there we have it. 1.5 is the midpoint between 0 and infinity. All right, that was a lot to take in. Let's recap what we did. First, we took the floating point endpoints of our range, which were the floating point numbers 0 and infinity, and we read these floating point numbers back as integers, which were 0 and 2.1 billion as integers. Remember that this process is not the same as casting to an integer, since what we did here is we directly read the bits of the floating point number as if it was an integer. We then found the midpoint by adding these two numbers and then dividing by 2. It's this 1.06 billion number as an integer. We then read this integer midpoint back as a floating point number, which is the exact opposite of what we did in step 1. And we got this floating point number 1.5. Using this process, you can show why the very next number expected, which is the midpoint between 1.5 and infinity, is this 1.67 times 10 to the power of 154, which is a very large number. However, note that Ruby uses 64-bit floating point numbers internally, which means that in order to calculate this by hand, you'll also have to use 64-bit floating point numbers. instead of 32-bit floating point numbers like the examples shown so far. But this is left as an exercise for you to do at home. All right, now you might be asking, why does this even work? Why can we read floating point numbers as integers and then perform binary search over it? Recall that the requirement to use binary search is that the list that is being searched on must be sorted in either ascending or descending order. Well, does reading floating point numbers as integers guarantee that it's sorted ascendingly? In other words, does a larger floating point number always result in a larger integer when that floating point number is read as an integer? Well, let's look at the parts of a floating point number again. The significand has 23 bits of the least significant digits. We know that a floating point number with the same sign and exponent but a larger significand will always mean a larger floating point number in magnitude. And a larger significand will result in a larger integer when we read it back as an integer. Okay, so what happens when we increase the exponent? Well, since the exponent determines the range that the floating point number is in, and since the ranges have no overlap, a larger exponent will always result in a larger floating point number in magnitude. And of course, this results in a larger integer when we read it back as an integer. Therefore, this satisfies the requirements of binary search, and this is why we can use this technique to binary search over floating point numbers. Let's take a look at the code in Ruby that implements the range B search method. The code is inside the Ruby source code, which is written in C. So it's unfortunately not as easy to read or understand as Ruby code. So I've simplified the code, and parts have been cut out for simplicity. Let's look at the function rangeBSearch that implements the Ruby method. It accepts one argument, which is the range we're binary searching over. We then get the two endpoints of the range, the beginning and the end. Let's look at the case when at least one of the two endpoints are floating point numbers, since this is the case that we care about. Using rFloat value, we get the C floating point value from the Ruby float object. The more interesting part to this line is the call to the double as int 64 function. Let's take a look at the implementation of that. We can see the implementation of it up here. It accepts a double precision floating point number and returns a 64-bit integer. So what does this function do? It first creates this local variable called convert, which is of this type called union int64 double. We can see the definition of this union at the top here. It's a union of either a 64-bit integer or a double precision floating point number. If you're not familiar with unions in C, it essentially lets you store any one of these data types at the same memory location. It's important to note that it lets you store any one of these data types and not all of them, meaning that the size of the union is only as large as the size of the largest element. In this case, since both of these types are 64 bits in size, the size of this union is also 64 bits, which is 8 bytes. Let's go back to the double as int 64 function. We then set the double member of the union. We're setting it to the absolute value of the floating point number using the fabs function. We're setting it to the absolute value due to differences in how integers and floating point numbers represent negative numbers. Integers represent negative numbers using the 2's complement, whereas floating point numbers only set the negative bit. For example, this means that for floating point numbers, 1.5 and negative 1.5 will only differ by a single bit, which is the sign bit. However, for integers, 10 and negative 10 will differ much more than a single bit. I won't be talking about what the 2's complement is and why integers use it today, but you can look into it if you're interested. So in order to not worry about this difference, we use the absolute value here. We then read the union back as an integer and setting it to negative as required. In the previous line, we set the union from the floating point number, and here we read it back as an integer. Note that we're doing this in order to not perform any casting, since casting will attempt to convert the floating point number into an integer rather than directly reading it as an integer. Now let's go back to the rangeBSearch function. We then perform binary search over the 64-bit integers, which were read from the floating point endpoints. All right, hopefully you followed along and have a high-level understanding of how this code works. If you're interested in playing around with floating point numbers, I highly recommend this site called float.exposed. It gives you lots of useful information about floating point numbers. On this site, you can see information such as the floating point value, the bits that represent this floating point number, the values of the sign, the exponent, and the significand as decimal integers, and the value of this floating point number when read as a hexadecimal or decimal integer. This talk was adapted from my blog post at this link, which you can also access through this QR code. Feel free to reach out to me through Twitter. My handle is peterzoot118. If you're in the future and watching a recording of this talk, hopefully Twitter is still alive by then. If not, you can always reach out to me through email. My email is peter@peterzoot.ca. Thank you for listening to my talk. We still have a couple of minutes. If anybody has any questions, you can ask them now, or you can always talk to me after this talk. I'll be around in the conference for the next 3 days. Yeah, so actually, right before this talk, Benoit and I actually looked at the implementation of this function. Sorry? Oh, I need to repeat the question. So the question was, why does Ruby specifically do this floating point to integer conversion instead of just directly searching over floating point numbers? And the answer is, Benoit and I actually looked at the implementation of this function in Truffle Ruby before this talk. And interestingly enough, because it's written in Ruby, it's so much more easy to understand in Ruby, and it doesn't do this kind of, you might call it a dirty trick. What they do instead is they first check if the number is infinity, and so then they know if it's infinity or not. And if it's not infinity, then they binary search between 0 and the largest floating point number possible. And then you can perform binary search because you can divide the largest floating point number by 2, whereas you cannot divide infinity by 2. And so Ruby could have done something like that, but because it's C, so they wanted to do this trick that is very clever, but instead is rather difficult to read and has seemingly arbitrary output. So here we have infinity, right? Infinity is 0 from the sign. The exponent is all ones and all 0 significand. For not a number, it is also so I have a pointer here if you can see it. The exponent is all ones, but we have a non-zero significand. So there's actually more than one way to denote not a number. In fact, here there would be 2 to the power of 23 minus 1 ways to denote not a number. Yeah, so the question was, why is there 8 million ways to denote not a number? And the answer to that is so you'll have to ask IEEE for that. Okay, the question was, do I think not a number should be a falsy value? And I'm assuming you mean that in Ruby. Yes. No, because this isn't JavaScript, so the only falsy value should be false and nil, and we don't need more falsy values. All right, thank you very much.